In November of 2020, an instrument anchored off the coast of Vancouver Island measured a single wave 17.5 meters high, rising out of a sea that was barely 6 meters tall, almost 3 times the size of everything around it. By the numbers, it was the most extreme rogue wave ever recorded, an event the math says should happen about once every 1,300 years. And here is the part almost no one is saying out loud. We have only been able to measure these waves at all for about 30 years. The very first one was caught by an instrument on the first day of 1995. So, inside a record barely 3 decades long, the ocean has already handed us a wave that is only supposed to appear once in 13 centuries. It is as if you started a stopwatch, and in the first 30 seconds you witnessed a thing that is only supposed to happen once every 20 minutes. Either we got impossibly lucky in our first half-minute of looking, or the clock we use to measure how rare these waves really are is simply wrong, and these are not gentle things. A wave like this one has the documented power to climb more than 20 meters up the side of a modern steel ship and tear the lifeboats clean off it. Vessels the size of small towns have vanished in the open ocean in a single night, leaving behind no wreckage and no survivors, while science insisted for centuries that such waves could not exist at all. But the part that should genuinely unsettle you is the timing. The most extreme wave on record arrived in 2020, and the force that drives the very worst of them, the wind, the warming, the changing temper of the sea itself, has not even fully arrived yet. The record broke before the trigger fired. That is the whole story tonight. Not a monster. A timeline that is running faster than it is supposed to, in a record so short we are still on the very first page of it. Sit with that for a second. Hey you, before we go out onto that water, do me a quick favor and hit the like button, and subscribe to Deep Blue Lab if you have not already. It genuinely helps this channel reach the people who find the deep ocean as fascinating and as quietly unsettling as we do. And drop a comment with where you're watching from. I love seeing how far across the world these stories travel, from how many different coastlines and time zones and dark bedrooms. Then settle in, turn the lights down low, and get comfortable. This is going to be a long, slow night out on the open sea. Now, let's get into it. Part 1. The wave that should not exist yet. Something is wrong with the timeline. Not the timeline of a single storm or a single season or even a single bad year out on the water. The timeline of the entire recorded history of the rogue wave. Because the most extreme one we have ever measured did not arrive at the end of a long, patient century of watching, the way you would expect a record to be quietly set and then broken. It arrived almost at the very beginning of our ability to watch at all, in a record that is barely old enough to drive a car. Let me take you back out to that buoy, because the details matter, and they only get stranger the closer you look at them. The place is called Amphitrite Bank. It sits about 7 kilometers off the town of Ucluelet, on the wild outer coast of Vancouver Island in British Columbia, where the open Pacific comes rolling in off thousands of kilometers of empty water and meets solid land for the very first time. There is nothing to slow that water down before it gets there. A swell born in a storm halfway to Japan can travel uninterrupted across the entire North Pacific and arrive at that coast with most of its energy intact. It is one of the rougher, more exposed stretches of coastline in all of North America. And moored out there, riding the swell, was a sensor buoy operated by a company called Marine Labs, one node in a growing network of instruments built for a single patient purpose: to sit in the water, day after day, and measure the exact shape of the sea as it passes underneath. On a day in November of 2020, that buoy was riding through a sea state with a significant wave height of about 6 meters. Now, I want to be precise about that phrase, significant wave height, because it runs through this entire story like a thread, and most people have never once heard it. It does not mean the single biggest wave out there. It means the average height of the largest 1/3 of the waves passing through over a given stretch of time. It is the number oceanographers use to describe, in one clean figure, how rough the sea actually is. So, when I tell you the significant wave height that day was 6 meters, I am describing a genuinely serious, dangerous sea, the kind of conditions a Coast Guard would warn small craft to stay out of. The waves themselves were already tall, and I want you to picture, for just a second, what that buoy was actually doing out there. Because it is a quietly heroic little thing. It is not much bigger than a person. It sits on the surface, rising and falling with every swell that passes, and inside it are instruments measuring its own motion many times a second. Up and down, all day and all through the night, in fog and in storm and in the long empty gray hours when nothing happens at all. It does not get tired. It does not blink. It does not look away at the wrong moment, the way a frightened sailor on a heaving deck might. It simply records, faithfully, the exact shape of the sea moving underneath it, and it sends that record home. And that, in the end, is the only reason we have this story at all. For thousands of years, the only witnesses to these waves were human beings, who were terrified, and who very often did not survive, and who, when they did, were not believed. This time the witness was a machine that felt no fear, and had no reason on earth to exaggerate. It just sat in the water, and it counted. And then a single wave came through that measured 17.5 meters. To understand why that one number stopped a room full of scientists cold, you have to sit with the ratio, not just the height. 17.5 meters, rising out of a 6-meter sea. That wave was very nearly 3 times the height of the significant waves around it. And the line the science draws, the rule that says when an ordinary big wave becomes a genuine rogue wave, is this: a wave only earns the name if it is more than twice the significant wave height. Twice is the threshold. Twice is already rare enough and dangerous enough to have its own name and its own field of study. This wave was not twice. It was almost 3 times. It did not just cross the line that defines a rogue wave. It cleared it by a margin that the textbooks did not really have a category for. That is exactly why Dr. Johannes Gemrich, a physicist at the University of Victoria who has spent a career studying the big waves that come ashore along the coast of British Columbia, did not reach for the word tallest. He reached for a more careful, more loaded word. In a peer-reviewed paper he published with his colleague Leah Saikon in the journal Scientific Reports in early 2022, he called the Ucluelet wave likely the most extreme rogue wave ever recorded. Most extreme because of that ratio, because of how absurdly far it reached above the sea that was supposed to be its natural ceiling. And then they did the piece of math that turns a strange measurement into something that genuinely keeps you up at night. They asked, given a sea state like the one off Ucluelet that day, how often should the ocean be physically able to produce a wave that far outside the normal range? Put a number on the rarity, and the number they arrived at was that an event like the Ucluelet wave should occur, in conditions like those, on the order of once every 1,300 years. Let that land for a second. 1,300 years. Go back 1,300 years from today, and you are in the early Middle Ages, before most of the cities you know existed, before the languages most of us speak had taken their modern shape. That is the recurrence interval. That is how rare the math says this wave should be. And we caught it, not on some heroic decades-long expedition to the most violent corner of the planet. We caught it on a routine November day, on a single buoy, off a small fishing town, in a measurement record that did not exist at all until 1995. I want you to really feel the strangeness of that, because it is easy to let a number like 1,300 years just slide past you. So think about the buoys themselves. There are only so many of them in the water, and they have only been out there, in any real numbers, for a couple of decades. Compared to the size of the ocean, a buoy network is almost nothing. It is a scattering of pinpricks across a surface that covers most of the planet. The overwhelming, staggering majority of the sea at any given moment has no instrument anywhere near it. So, for one of those few pinpricks to be sitting in exactly the right spot, on exactly the right day, at exactly the right second, to catch a wave that is only supposed to come along once in 13 centuries, the luck involved is almost absurd. Unless, of course, it is not luck. Unless these waves are simply far more common than the 1,300-year figure suggests, and a network that catches almost nothing still managed to catch one. Because there are so many more of them out there than we ever allowed ourselves to believe. This is the paradox we are going to spend the next while inside of. So I want you to hold on to it the way you would hold on to a railing on a pitching deck with both hands. The rarest wave we have ever documented showed up almost at the start of our ability to document waves at all. And every single thing we are about to talk about tonight. The ships that vanished without a trace. The strange and simple physics that builds a monster out of an ordinary sea. The quiet trend that has scientists genuinely uneasy. All of it flows back to this one central impossibility. The clock that is supposed to measure how rare these waves are appears to be running fast. The record broke before it had any business breaking. And if that does not unsettle you yet, wait until you hear how short the record actually is, and how violently the ocean had to argue with us before we were willing to believe these waves were real at all. Because here is the thing about that 1,300-year number. It is not a prophecy. It is a confession. It is the mathematics quietly admitting that our models of how the ocean behaves did not expect a wave like this, and the ocean went ahead and made one anyway. A once-in-1,300 years wave is not, in the end, really a statement about the wave. It is a statement about the size of our ignorance. It is the gap between what we predicted and what actually happened, written out as a number. And the honest scientists, the ones publishing in the journals rather than chasing a headline, are the first ones to tell you so. So, before we go any deeper, let me ask the question that sits underneath this entire night. If the most extreme wave on record arrived this early, in a record this short, what does that quietly tell us about all the waves we have not measured? About the ones that came through in the dark, in the middle of the ocean, with no buoy underneath them and no one left alive to write them down. Think about what it means to set a world record on your very first lap. It almost never means you happened, by pure luck, to witness the single rarest event possible in your first 30 years of looking. It usually means something much simpler and much more unsettling. It means the thing is more common than you thought, and you had simply never built the eyes to see it. And for almost all of human history, we had not. We were blind to these waves entirely. The story of how we finally opened our eyes does not begin with a triumph. It begins with a number that nobody wanted to believe, and a standoff between sailors and scientists that lasted, almost unbroken, for thousands of years. Part 2. The 30-Year Record. To really understand why a single wave off Vancouver Island matters so much, you have to understand how recently we learned to see these waves at all. And the honest answer is going to surprise you, because the gap between the moment sailors first started reporting rogue waves and the moment science finally accepted they were real is one of the longest, strangest standoffs in the whole history of human knowledge. For as long as people have gone to sea, they have come back with the same story. A wave that did not belong. A wall of water out of a sea that did not justify it. A sudden mountain rising in an ordinary swell. A trough that opened first, like a hole punched in the surface of the ocean, and then a crest behind it that blotted out the entire horizon. People told these stories for thousands of years, in every seafaring culture on Earth. In every century there were ships. There is an account from the third voyage of Christopher Columbus in 1498, in which his crew heard a tremendous roar and saw a wave they described as tall as the ship's masts, a wave that lifted the vessels higher than anything those experienced sailors had ever felt, and then dropped them down into an enormous trough. The stories were not rare, and they were not vague. They were everywhere, and they were specific, and science did not believe a word of it. I want to be honest about how total that disbelief was, because it is the key that unlocks this entire part of the story. The standard mathematics of ocean waves, the model the whole field of oceanography ran on through most of the 20th century, treated the surface of the sea as a sum of ordinary waves, whose heights followed a tidy, well-behaved statistical curve. And under that math, a truly giant wave, a wave of 25 or 30 meters, was not merely rare. It was so rare as to be effectively impossible. The numbers said a wave like that should appear at any given spot in the ocean, maybe once in 10,000 years, maybe once, somewhere on the entire planet, across many decades. By the book, a wave that big was a unicorn, a thing that did not really happen. So, when a sailor came back to port and swore he had seen a 100-foot wall of water rise up and nearly take his ship, the science had a ready and gentle answer. It said, in so many words, that he was mistaken, that fear and darkness and a violently heaving deck had stretched a large but ordinary wave into a tall tale. The reports were quietly filed under folklore, in the same drawer as sea serpents. Almost nobody in the field took them literally. And that is how things stood, decade after decade, for most of the 20th century. Sailors insisting, scientists dismissing, and no way on earth to settle the argument, because you cannot prove the existence of a thing that rises out of the sea, exists for a handful of seconds, and then vanishes completely, leaving no trace behind but a frightened story. And I want you to sit with the human cost of that standoff, because it is easy to talk about it as a dry scientific disagreement, and it was not. Think about what that disbelief actually meant out on the water. It meant that for generations, the ships being built, the offshore platforms being designed, the safety margins being calculated, were all built on the assumption that the giant wave was a myth. Engineers designed hulls and bridges and superstructures to survive the biggest wave the accepted math allowed for, and not 1 meter more, because the math told them anything bigger was a fairy tale. So when one of these waves did come, and it found a ship that had been built in good faith by smart people to survive a sea that could not officially exist, the result was not a near miss. It was a vessel that simply was not strong enough, meeting a force that was not supposed to be possible. The disbelief did not just live in textbooks. It was welded into the steel, and the people who paid for it were the ones who took those ships out and did not come home, and were then quietly remembered as victims of ordinary bad weather, because the alternative was a wave the science refused to name. And then, on the first day of 1995, the argument ended in a single instant, on an oil and gas platform in the middle of the North Sea. The platform was called Draupner E. It stood in the North Sea about 160 kilometers off the southern tip of Norway, part of a complex that supported a gas pipeline. And mounted on the underside of it, pointing straight down at the water, was a laser, a downward-facing laser rangefinder, installed for the dull, practical job of measuring the distance to the sea surface. It had no opinions and no imagination. It simply ticked away through the winter, logging the rise and fall of the waves passing below, second after second after second. On the afternoon of the 1st of January, 1995, in the middle of a serious winter storm, that laser recorded something the textbook said could not happen. A single wave, rising 25.5 meters from its trough to its crest. The crest alone stood more than 18 meters above the still water level, the height of a 6-story building of water heaped above where the surface should have been, and it came through a sea whose significant wave height was about 12 meters. Twice the surrounding sea, the exact textbook definition of a rogue wave, captured not by a terrified sailor on a pitching deck, but by a cold, indifferent instrument with no capacity whatsoever to exaggerate. This is the moment our record actually begins. Not in antiquity, not even in the early 20th century, on the first day of 1995. That is the day the rogue wave stopped being folklore and became data. And I want you to really feel how recent that is, because it reframes everything. There are people watching this right now who are older than the entire scientific record of rogue waves. The whole archive, every confirmed measurement, every careful number we are discussing tonight fits comfortably inside a single human lifetime, and the great bulk of it inside 30 years. What made the Draupner measurement impossible to wave away was a second, quieter piece of evidence. High up on that platform, far above the level any normal wave should ever be able to reach, there was minor damage. Equipment struck by water that simply should not have been able to climb that high, so the laser said a monster had come through, and the steel of the platform itself, scarred above the waterline, agreed with it. This time there was no frightened sailor to second-guess. There was a precise instrument, and there was a physical wound on a man-made structure, both telling exactly the same story. The thing science had dismissed for centuries had just signed its name on a gas platform in the North Sea. And here is a detail to hold on to, because it is going to matter a great deal later in the night. The Draupner wave did not appear in calm water out of nowhere. It came in the middle of a serious winter storm, in a part of the sea where that day the conditions were unusually complicated. Years later, when scientists went back and reconstructed exactly what the sea was doing around that platform on the 1st of January, 1995, they found signs that more than one wave system was present at once. Different trains of waves, moving in different directions, sharing the same patch of stormy water. Tuck that away, because when we get to the question of how the ocean actually builds one of these monsters, that detail, the idea of two seas crossing each other in a storm, is going to turn out to be one of the central keys to the whole thing. The very first wave we ever measured was already quietly showing us its secret. We just did not know yet how to read it, And once scientists had one confirmed wave in hand, they did the thing scientists always do next. They went looking for more. And what they found blew the old mathematics wide open. In the early 2000s, the European Space Agency, working through a research project called MaxWave, set out to do something that had simply never been possible before in human history. They used radar instruments aboard 2 satellites, a pair of European radar satellites, to look straight down at the surface of the open ocean from orbit, and to hunt for giant waves across the entire globe at once. No ship can do that. No buoy can do that. Only a machine in space, sweeping its radar across the whole sea. The project was led by Dr. Wolfgang Rosenthal, and the question driving it was beautifully simple. If Draupner was real, then how often does this actually happen out there, across all the vast stretches of ocean that no human being is watching? They analyzed 3 weeks of satellite data. Just 3 weeks. And in that small window, scanning the world's oceans from space, they identified more than 10 individual giant waves, each one over 25 meters tall, scattered across the planet. Think about what that single number did to the old picture of the world. The accepted statistics had said one such wave, somewhere on all of Earth, every several decades. The satellites found more than 10 of them in 21 days, not across a lifetime, across 3 weeks. Rosenthal put it as plainly as a scientist can. The fact that these waves take place relatively frequently, he said, carried major safety and economic implications, because the ships and the offshore platforms of the time were built to withstand maximum wave heights of only about 15 meters. 15. And the ocean, it turned out, was routinely throwing up walls of water nearly double that height, all over the world, all the time. We had simply never had the eyes in the right place to count them. So here is where Part 2 leaves us, and it is worth saying slowly and out loud before we go any deeper. Our record of rogue waves is about 30 years old. Inside that short window, we have confirmed beyond any doubt that they are real. We have learned that they are far, far more common than the old math ever allowed. And we have already caught the single most extreme one we have ever seen. Every one of those 3 facts points in the same uncomfortable direction. We are not looking at a rare, stable, well-understood phenomenon that we have had a handle on for a long time. We are looking at something we have only just learned to see, that is both more frequent and more violent than we expected, captured in a record so young that we genuinely cannot yet know what its true ceiling is. And to understand why these waves are so much more common than the mathematics predicted, you have to understand the one thing that old mathematics left out. You have to understand how the ocean actually builds a monster. Part 3. How the ocean builds a monster. For decades, the central mystery of the rogue wave was not whether they happened. After Draupner, after the satellites, that was settled. The mystery was how. How does an ordinary, if rough, sea suddenly gather enough energy into one single spot to throw up a wave 2 or 3 times the size of its neighbors, and then, a few seconds later, let it dissolve back into the swell as if nothing had ever happened? Where does all that energy come from, and why does it arrive at the same place at the same instant? That is the question. And I want to be precise here, because this is the part of the story where the science has genuinely changed its mind in the last few years, and the new answer is at once simpler and stranger than the one we used to give. Let me start with the explanation you have most likely heard before, because for a long time it was the undisputed star of the show. It even has a proper name: modulational instability. Some scientists call it the Benjamin Fair instability, after the two physicists who first described it. And the idea runs like this. In a train of steep waves all marching in roughly the same direction, the waves do not stay neatly, evenly spaced. Tiny irregularities in the train begin to feed on themselves. One part of the group quietly steals energy from the parts around it, growing taller while its neighbors shrink, until for one brief moment the energy of a whole long stretch of sea has been funneled into a single towering peak. And then it collapses back, and the energy spreads out again, and the sea looks ordinary once more. Physicists can produce this effect beautifully in a long, narrow wave tank. They can even produce the very same mathematics in pulses of light traveling down an optical fiber, which tells you it is a deep and general feature of how waves behave, not just some quirk of water. For years, that was the headline explanation. The rogue wave as a kind of self-focusing instability. The sea, for a moment, hoarding its own energy into one deadly spike. It is elegant. It is the kind of clean, almost beautiful mechanism that makes for a wonderful story. But here is the honest update, and it genuinely matters. When scientists went out and looked for modulational instability in the real open ocean, it largely was not there. The effect that works so cleanly in a long, straight, one-directional tank turns out to be much weaker in a real sea for a simple reason. A real sea is a mess. The waves are not marching obediently in a single direction. They are arriving from many directions at once, a chaos of overlapping trains crossing and interfering. And that directional spreading drains away the delicate, self-focusing effect almost entirely. A peer-reviewed study by Francesco Fedele and his colleagues, published in Scientific Reports in 2016, made the argument right there in its title, that real-world ocean rogue waves can be explained without the modulational instability at all. The lab darling, it turned out, was mostly a creature of the lab. So what is actually building these waves out there, in the real water? And the answer the field has increasingly settled on is almost disappointingly simple. Right up until you sit with it for a moment, and then it quietly becomes the most unsettling part of the entire night. The main driver is something called linear superposition. And all that grand-sounding phrase really means is this. The surface of the ocean at any given moment is the sum of an enormous number of different wave trains, of different sizes and speeds and directions, all passing through the same patch of water at the same time, all adding themselves together. Most of the time, they add up into the ordinary lumpy chaos we simply call a rough sea. The crests and the troughs of all those different trains are scattered and out of step, some lifting the water, some pulling it down, mostly canceling one another out. But every so often, by pure chance alignment, a large number of those separate crests happen to arrive at the same point at the very same instant. And they stack, crest on top of crest on top of crest. For a few seconds, the water at that one spot rises into a wave far taller than any of the individual trains that built it. And then the alignment passes. The crests fall back out of step, and the monster is simply gone, dissolved back into the sea that made it. That is the mechanism. Not a mysterious instability secretly hoarding energy. Just an unlucky, perfect, fleeting moment of addition. A coincidence of timing, written across kilometers of open water, that happens to land all its weight in one place. And I want you to sit with how strange it is that the answer is so ordinary, because there is something almost unsettling about it. We wanted the rogue wave to have an exotic cause. We wanted it to be a special kind of wave, born from some rare and dramatic instability, a monster with its own private physics. That would have been comforting in a way, because a special cause is a rare cause, something you could hope to avoid. But the truth the data keeps pointing to is the opposite, and it is colder. There is nothing special about a rogue wave at all. It is made of exactly the same ordinary waves that are out there every single day, in every sea on Earth. It is just those ordinary waves, briefly, catastrophically in step. Which means the ingredients for a monster are present, always, everywhere there are waves. The sea does not need to do anything unusual to build one. It only needs its ordinary chaos to line up the wrong way for a few seconds. And ordinary chaos, given enough ocean and enough time, will always, eventually, line up. Now, this is not some fringe idea on the edge of the field. In 2023, a team led by Dion Hefner at the Niels Bohr Institute in Copenhagen, working alongside Johannes Gemrich, the same physicist behind the Ukulele wave, and Marcus Joachim, did something genuinely remarkable to test it. They took the records from a network of 158 wave buoys, positioned around the coasts of the United States and its territories. They fed a machine learning system more than 1 billion individual waves, the equivalent of roughly 700 years of ocean observation, all compressed into a single vast database. And then they asked the artificial intelligence to find, from the raw data alone, with no theory whispered in its ear, what conditions actually come before a rogue wave. What came back, in a paper published in the Proceedings of the National Academy of Sciences, was not modulational instability. It was linear superposition. The dominant cause of real rogue waves, the data itself said, is simply that ordinary wave systems happen to line up, as Hefner described it. If two wave systems meet at sea in a way that increases the chance of high crests followed by deep troughs, the risk of an extremely large wave arises. That is the whole secret. There is no monster lurking down in the physics. There is just the ocean occasionally, by chance, adding itself up wrong. And what is genuinely lovely about that study is the form the answer took. The team did not just get a prediction out of the machine. They distilled the artificial intelligence down into a clean, readable 5-part equation. As Joachim put it, machine learning is usually a black box that does not increase human understanding, but in this case they used it to transform an enormous database of observations into a new equation a person could actually read. Hold on to that. We will come back to it at the very end of the night, because it is the hinge the whole story turns on. But the engine is only half the picture. Because there are conditions out there that load the dice. Conditions that make those deadly, perfect alignments far more likely than pure chance would suggest. And this is where the night turns from a physics lesson into something with teeth. The first is crossing seas. And this is one of the most beautiful and frightening pieces of recent research, because scientists actually rebuilt the Draupner wave with their own hands in order to find it. A team from the University of Oxford and the University of Edinburgh, led by Dr. Mark McAllister and Professor Ton van den Bremer, went into a remarkable circular wave tank in Edinburgh called Flow Wave, a tank with wave makers arranged all the way around its circular edge, so that they could send waves in from any direction they chose. And they set out to recreate the exact Draupner wave from 1995. For a long time, they could not do it. Whenever they sent their waves in from a single direction, the wave would start to grow, and then it would break, foaming and collapsing into white water before it could ever reach monster height. The breaking acted like a hard ceiling. The wave was not allowed to get that big. And then they found the trick. They could only build the Dropner wave when they sent two wave systems crossing each other at an angle of about 120 degrees. At that steep crossing angle, something fundamental changes in the way a wave breaks. The usual ceiling lifts. The wave is suddenly able to climb far higher before it collapses because the two crossing systems are, in effect, holding it up in a way that a single direction never can. And when they finally got it right, the shape of the wave standing in their tank looked uncannily like the great cresting wave in Hokusei's famous Japanese print, the one with the curl of foam reaching over like a claw above the little boats. The single most famous image of a monster wave in all of human art, quietly reproduced in a laboratory in Edinburgh, at a crossing angle of 120 degrees. Now, think about what that means out in the real ocean. Crossing seas are not exotic. They are not rare. They happen constantly. Whenever a fresh storm sends its waves across the leftover swell of an older one, whenever the wind shifts a direction, whenever two separate weather systems happen to share the same patch of sea, and wherever two wave fields cross at a steep angle, the ocean's own safety valve, the braking that normally limits how tall a wave is allowed to get, is partly switched off. And the giants become possible. The second condition that loads the dice is current. Where waves run head-on into a strong ocean current, the current squeezes them, concentrating their energy the way a glass lens concentrates sunlight into a burning point. The classic place this happens, the most notorious place on Earth for it, is the Agulhas Current, off the southeast coast of South Africa, where a powerful, warm current sweeps to the southwest, directly into the path of the great swells rolling up from the Southern Ocean. In that head-on collision zone, ordinary waves get focused into extraordinary ones, and the sea there has, on occasion, thrown up walls of water more than 30 meters high. It is one of the single most dangerous stretches of water on any major shipping route in the entire world, and it is dangerous for exactly this reason. A current, acting as a lens for wave energy. Hold on to the Agulhas, because in a few minutes it is going to have a body count. And the third condition, the one that has only just been confirmed, and the one that points straight at the future, is wind. For a long time, wind was treated as the slow background hum that builds ordinary waves over hours and days. The patient cause of the everyday sea, not the sudden trigger of the giants. That picture changed in 2024. A team led by Professor Alessandro Toffoli at the University of Melbourne did something that almost nobody had managed before. They took their instruments directly into the Southern Ocean itself, the stormiest, most relentlessly wave-battered water on the entire planet, aboard a research vessel pushing through the seas that ring Antarctica, and they measured rogue waves as they actually formed, in the wild, in real time. What they found was striking, and it should stay with you. In young seas that were still being actively driven and whipped up by strong wind, rogue waves appeared roughly once every 6 hours. Once every 6 hours. And in mature seas where the wind had died away and the waves were simply rolling on under their own momentum, they found essentially none. The wind itself, the active forcing, the storm doing its work in the moment, was the thing producing the monsters. As Toffoli described it, the wind creates a chaotic situation, where waves of many different sizes and directions coexist all at once, which is to say, the wind manufactures exactly the messy, crossing, overlapping conditions that make a deadly alignment likely in the first place. It was the first time anyone had truly validated, out in the open ocean and not just in a tank or a computer. That wind is not merely the slow builder of the everyday sea. It is the direct trigger of its very worst waves. And now, hold those three conditions together in your mind all at once: crossing seas, opposing currents, and strong, active wind. Because in the final stretch of this story, when we get to what the scientists are actually worried about, every single one of those dials is wired to a world that is changing. The mechanism that builds a rogue wave is just ordinary alignment, blind chance, but the conditions that load the dice are precisely the conditions that a warming, windier, more energetic ocean produces more of. The trigger, in the end, is the weather. And the weather, as you well know, is not staying still. Part 4. The Ships That Vanished. I have given you the physics. Now I have to give you the cost. Because the real reason rogue waves stopped being a quaint scientific curiosity and became a thing that serious investigators take seriously is not a number printed in a journal. It is a long, quiet list of ships that went out onto the water and never came back, and the slow, dawning realization that something out there had been killing them all along, methodically, for generations, and that we had been writing it off the whole time as nothing more than bad weather. I want to be careful and honest in this part, more careful than most documentaries bother to be, because the ocean very rarely leaves proof. When a ship goes down in the open sea, it almost always takes the evidence down with it. So nearly everything I am about to tell you is the most accepted theory, the strongest available interpretation of a few scattered fragments, and not a hard certainty. I am going to tell you what we found, and I am going to tell you what it most likely means. And I am going to be clear about the difference between the two every step of the way. Keep that distinction in your mind as we go, because it is exactly the kind of honesty this story deserves and rarely gets. Let me start with a single case that, more than any other, forced the science to finally take rogue waves seriously. The München. The München was a German cargo ship. A large, modern, exceptionally well-built vessel, a type called a lash carrier, designed to carry whole loaded barges across the ocean. In December of 1978, she left the German port of Bremerhaven, bound for Savannah on the American East Coast, carrying a cargo of steel and a crew of 28. She was not some fragile, aging tramp steamer. She was one of the most advanced cargo ships of her entire era, and her crew were experienced North Atlantic sailors who knew exactly what a winter storm out there could do, and had crossed through plenty of them before. On the night of the 12th of December, somewhere out in the middle of the Atlantic, in the teeth of a severe storm, she began sending out garbled, broken distress signals. And then nothing. Silence. By the time the largest sea search the world had ever mounted up to that point had finally wound down, not one of the 28 crew had been found. The München was simply gone, erased from the surface of the ocean, with almost nothing left to say what had happened to her. What she did leave behind is the part that haunts. Among the very few pieces of wreckage ever recovered was one of her starboard lifeboats. Now, that lifeboat had hung from its davits, the steel arms that hold a lifeboat snug against the side of a ship, about 20 meters above the waterline. 20 meters. The height of a 6 or 7-story building above the sea. And when investigators examined that recovered lifeboat, they found something that should not have been possible. The pins that held it, which under any normal circumstance should have been hanging straight down toward the water, had been bent backward, bent from the front of the ship toward the rear, by some tremendous force that had struck the lifeboat from forward, run the length of the ship, and torn the boat clean from its mountings. Think about what that single detail actually requires. For something to reach a lifeboat hanging 20 meters above the water, and to strike it hard enough to bend its solid steel mounting pins from front to back, the sea had to reach up 20 meters into the air and hit the ship a forward blow like the swing of a hammer. The official inquiry, working at a time when rogue waves were still regarded as very nearly impossible, could only conclude that the severe weather had somehow produced an unusual event that overwhelmed the ship. They did not yet have the language for what they were looking at. They did not have the concept. But years later, with everything we have since learned, the most accepted interpretation is that the Moonchen met one or more rogue waves. A wall of water that came up and over her bow, smashed her bridge and her controls high above the deck, and left her wallowing, blinded and helpless, until the storm finished the job. She is, in a very real sense, the ship that taught science to believe. The bent pins on that lifeboat were a fingerprint, and it took us years to learn how to read it. And I want you to stay with the Moonchen for one more moment, because there is something about her that should genuinely change how you picture all of this. We tend to imagine that disasters at sea belong to a rougher, older age, to wooden ships and oil lamps and men who did not have radar or radio or accurate forecasts. The Moonchen had all of those things. She was modern. She was huge. She was crewed by professionals who had crossed that ocean many times and knew exactly what they were doing. She sent distress calls, which means that right up until the end, there were people on that bridge working the problem, doing everything right. And it was not enough. Something came out of the dark in the middle of the 20th century, with all of our technology aboard, and it took a ship the size of a small town and 28 capable people and left almost nothing behind. That is the part that should sit with you. Not that the sea was dangerous long ago, that the sea is still, right now, with all our instruments and all our confidence, fully capable of reaching up 20 meters in the dark and erasing a modern ship as if it had never existed. And the Moonchen was very far from alone, because there is one particular stretch of ocean that has been quietly doing this for a very long time. The Agulhas Current, off South Africa, the lens we talked about back in Part 3. That coast sits squarely on the main shipping route between the oil fields of the Middle East and the markets of Europe and the Americas, which means enormous ships, supertankers among them, have been passing directly through that focusing zone for decades. And the toll there is, unusually, documented. By one accounting, around 30 large ships were seriously damaged or outright sunk by giant waves along the southeast South African coast in the single decade between 1981 and 1991. 30 large ships in 10 years, in one stretch of water, because a current was bending ordinary swells up into walls. The danger of the Agulhas was so consistent, so reliably deadly, that mariners learned to fear and respect it long before any scientist could explain why it happened. And the older losses there stretch back much further still. The SS Waratah, a large passenger and cargo steamer, vanished off that very same coast in 1909 with 211 people aboard, and was never found. One of the leading theories, never proven and never provable, is that she met a giant wave in a storm and was simply gone in a matter of moments. 211 people, and no wreck, no survivors, no answer. Just a coast with a long and terrible reputation. Now I want to widen the lens for a moment, because the true scale of this is larger than any single famous wreck. When the European Space Agency was making its case for studying rogue waves from orbit, It put the stakes in stark, sobering terms. Severe weather, the agency noted, had sunk more than 200 supertankers and container ships, vessels over 200 meters in length, in the previous 2 decades alone. Now, I want to be honest. That figure is for severe weather broadly, not for rogue waves alone, and the difference matters. But the point the agency was driving at is the one that should stay with you. Big ships, modern ships, the kind we quietly assume are simply too large, too solid for the sea to ever take. They do go down with a disturbing regularity, and a real share of those losses carry the unmistakable fingerprint of a wave that came up out of nowhere. These are not wooden sailing ships from a distant century. These are steel giants, the size of buildings laid on their sides, and the ocean takes them anyway. But the cases that hit the hardest, the ones that truly stay with you, are the ones with witnesses. Because rogue waves do not only sink anonymous cargo ships out in the empty dark. Sometimes they strike ships full of people, and sometimes those people live to describe exactly what they saw. In September of 1995, the very same year as the Dropner measurement, the great ocean liner Queen Elizabeth II was crossing the North Atlantic during a hurricane when a wave estimated at around 27 meters, roughly 90 feet, rose up directly in front of her out of the storm. The captain later described it as looking like the white cliffs of Dover coming straight at the ship, a literal, sheer white wall of water standing in the liner's path. She rode up and over it, and survived with only minor damage, but the people aboard had looked a true rogue wave directly in the face, and lived to tell it. Others were not so fortunate. In April of 2005, the cruise ship Norwegian Dawn off the coast of Georgia was struck by a series of waves about 21 meters tall, around 70 feet, that smashed windows on the 9th and 10th decks. Decks that sit far, far above the normal reach of the sea, high up where passengers feel completely safe. Cabins flooded. Several passengers were injured. In March of 2010, the cruise ship Louis Majesty, sailing in the western Mediterranean off the coast of Spain, was hit by a succession of abnormally high waves that broke clean over the 5th deck, shattered the glass, and killed 2 passengers, injuring several more. And in late 2022, the expedition cruise ship Viking Polaris, crossing toward the southern tip of South America on its way to Antarctica, was struck by a rogue wave that broke the windows of a passenger cabin and killed 1 person, an American woman, injuring 4 others. The investigators who looked into it noted, soberly, afterward, that abnormally large waves are simply a regular feature of that violent stretch of ocean. Not a freak. A regular feature. I want to pause on something here, because it is easy to blur all of these together, and one of them is a genuine trap that catches a lot of people. You may have heard of another Viking ship, the Viking Sky, which made dramatic headlines around the world in 2019 when it lost power in heavy seas off the coast of Norway and very nearly drove onto the rocks, before helicopters lifted hundreds of terrified passengers off the pitching deck one by one through the night. That was a harrowing event. But it was not a rogue wave. It was an engine failure in rough weather. And I mention it precisely because it is so often confused with the rogue wave cases, lumped in with them in articles and videos. The honest version of this story has to keep them separate. The real rogue wave deaths are unsettling enough on their own, without borrowing the wrong disaster to pad the list. And then there is the oldest layer of all, the part that lived in the folklore of sailors for centuries before any of these modern ship names ever existed. because the mariners had words for these things long before science deigned to. They spoke of the Three Sisters, a set of three giant waves arriving back to back, where a ship might just survive the first, then take the second full on the deck before it has managed to shed the water of the first, and then be driven straight under by the third piling its weight on top of all that accumulated water. They spoke of a hole in the sea, a sudden deep trough that opens up just before the wave, so that a ship first falls into a pit and then is faced, at the bottom of it, with a wall. And that detail, the hole that comes first, turns out not to be a frightened exaggeration at all. In 2012, researchers confirmed that rogue holes, deep and sudden troughs that are the mirror image of rogue waves, are a real phenomenon that the ocean genuinely produces. The sailors, it turns out, had been describing the physics accurately for hundreds of years. We simply had not been listening, the same way we had not believed the crew of Columbus in 1498, when they came home and described a wave as tall as the masts. So here is where Part 4 leaves us, and I want to lay it out plainly because the weight of it matters. The cost of these waves is not theoretical. It is not a thought experiment. It is the Moonshen and her 28 souls. It is 30 ships in a single decade off one African coast. It is the Waratah and her 211. It is broken windows 10 decks up, and passengers killed in their cabins on cruise ships within the last 20 years, in our own time, on ships people boarded for a holiday. And every single one of those losses was, for a very long time, written off as ordinary bad weather, because we did not yet possess the one concept that would have named the real killer. The ships were telling us, in the only language they had, the exact same thing the buoy off Ucluelet would eventually tell us, the same thing the satellites told us from orbit. These waves are real. They are far more common than we let ourselves believe, and we have spent almost the whole of human history refusing to see them. The only thing that has truly changed is that, finally, we can. And that brings us to the hardest part of this entire story. The part that is genuinely new, that is unfolding right now, and that almost no one is talking about. What happens to all of this in an ocean that is changing? Part 5. The pattern no one is talking about. This is the part of the night I have to handle most carefully of all, because it is exactly where a story like this usually goes wrong. It is very easy and very tempting to stand here and tell you that rogue waves are happening more and more often, that the ocean is somehow turning against us, that the giants are multiplying year on year. That version would be dramatic. It would also not be honest. And the honest version turns out to be stranger and quieter, and in the end, far more interesting than the scary one. So let me be precise about what the data actually says, because the whole truth lives inside a distinction that most people never hear. The difference between how often these waves happen and how extreme they are when they do. Those are two completely separate questions. And when you ask them separately, the answers point in opposite directions. In 2019, a team of researchers, A.D. Cattrall and colleagues at the National Oceanography Center in the United Kingdom, published a study in the journal Scientific Reports that did something patient and unglamorous and genuinely valuable. They took more than 20 years of data, gathered from 15 wave buoys strung out along the western seaboard of the United States, records running from 1994 all the way to 2016, and they went looking for trends. Two trends in particular. Are rogue waves on that coast becoming more common over time, or less? And, separately, are the ones that occur becoming more severe or less. And the two answers came back facing in opposite directions. Here is the first finding, and it is the one the scary version of this story always quietly leaves out. The frequency of rogue waves on that coast was, for the most part, going down. Not up. Down. At several of the buoys, the rate at which rogue waves occurred was actually declining slightly over the decades, by something on the order of 1.5% a year at some locations. So, no, I'm not going to stand here and tell you these waves are happening more often. Along the best studied coast we have, by the best long-term measure we have, they were happening, if anything, a little less often as the years went on. I would rather give you the number that is true than the one that sounds frightening. But here is the second finding. And this is the one that should hold your full attention, because it is the real story. While the waves were becoming slightly less frequent, the ones that did occur were becoming more severe. The study measured what it called an index of abnormality. Essentially, how far a rogue wave overshoots the ordinary sea around it, that very same ratio that made the Ucluelet wave so remarkable, the amount by which the giant towers over its neighbors. And that severity was increasing, by more than 1% a year at some of those locations. So, put the two findings together and look at the shape of it. The waves were getting rarer and bigger, less frequent and more extreme. Fewer monsters overall, but the monsters that did come were more monstrous than before. Sit with that distinction for a moment, because it is the entire heart of the pattern. If you only ask the ocean how often, you get a reassuring answer and you go back to sleep. If you ask it how bad, you get a worrying one. And the public conversation, on the rare occasions it happens at all, only ever asks how often. Almost nobody is asking how bad, which is precisely how the single most extreme rogue wave ever recorded can come through off Vancouver Island in 2020 and barely register in the news. We were all watching the wrong number, and think about why that distinction matters so much, beyond just being a nice statistical subtlety, because it matters in steel and in lives. A ship does not care, in the end, how often rogue waves happen across a decade. A ship cares about the single biggest wave it will ever meet. If the giants are growing more extreme, then the worst wave a vessel might encounter on a given crossing is growing too, even if such encounters are becoming rarer overall. The danger is not really about frequency. It never was. It is about the ceiling. It is about how high the very worst wave can reach, because that is the wave that decides whether a hull holds or fails, whether a bridge window survives or shatters 10 decks up. And the ceiling, the data quietly tells us, is the thing that is rising. Fewer rolls of the dice, perhaps, but loaded, more and more toward the catastrophic end. That is a far more dangerous shape for a trend to take than simple frequency ever would be. There is a second piece of that same study worth holding on to, because it tells you these waves have a season. The buoys showed, clearly, that rogue waves were far more likely in winter than in summer. In some places, nearly twice as likely in the winter months, and that is not a coincidence or a quirk of the data. Winter is when the storms are strongest, when the wind blows hardest and longest, when the seas are youngest and most chaotic and most crossed by competing swells. Now remember Toffoli's finding from the Southern Ocean, the one from Part 3. Rogue waves appear in young, wind-driven seas roughly once every 6 hours, and almost never in calm, mature ones. The winter spike that Cottrell's team found in the buoy data is that exact same truth, just written across the calendar instead of across a single storm. The dial that controls the very worst waves is wind, and wind has seasons, which raises the obvious uncomfortable question that this whole part has been walking toward. What happens to that dial on the largest scale in a changing climate? And here is where I have to be honest about the limits of what we actually know, while being just as honest about which direction the evidence leans. We cannot tell you exactly how rogue waves will behave 50 or 80 years from now. No one can. But we can tell you, with real confidence, what is happening to the conditions that load the dice, and that picture is not a reassuring one. Peer-reviewed projections of future ocean waves, the ones looking ahead toward the end of this century, find that extreme wave energy is expected to grow. One major study projected that the most extreme waves could increase by something in the range of 5 to 8% by the year 2100, driven primarily by stronger winds blowing across the oceans. And critically, that increase is not spread out evenly across the globe. The single region projected to see the most robust rise in extreme wave height is the Southern Ocean. The same violent band of water where Toffoli's team measured a rogue wave every 6 hours. The same place where the wind never truly rests. Some projections show local increases in extreme wave height there of more than 2 meters. Think about that. The stormiest ocean on the entire planet, the one that already manufactures these waves on something close to an industrial schedule, is the one that is expected to get stormier still. And I want to be careful with what I mean by the forcing is still building, because it is the single most important idea in this entire part, and it is easy to hear it as vague. It is not vague. It means something specific. The wind that drives these waves draws its energy from the difference in temperature across the ocean and the atmosphere, and that whole engine is changing as the planet warms. The projections do not say a switch will flip and the giants will suddenly arrive. They say the engine is being slowly turned up, decade by decade, and that the places where it was already running hottest, the Southern Ocean above all, are the places where it will run hottest of all. So, when I say we are still early, I mean it almost literally. The conditions that produced the most extreme wave on record in 2020 were the conditions of an ocean that has only just begun to feel the full push. We are reading the opening lines of something, and the worst of the forcing, by every projection we have, is still ahead of us, not behind. That is what makes the Ucluelet wave feel less like a freak and more like a warning shot. Remember how the drought broke its record before the El Niño that was supposed to cause it had even arrived. This is the same uncanny shape. The ocean set its most extreme mark on record, while the thing that is supposed to drive such marks was still warming up. The record came in during the pre-show, before the main act had taken the stage. And if that is genuinely what we are looking at, then the most extreme wave in recorded history is not the ceiling. It is the floor. It is the quietest version of what is coming, not the loudest. Hold on to that, because it is the heart of why this matters. Now take that and stack it on top of the mechanism from Part 3, and watch how the pieces lock together. The engine of a rogue wave is the chance alignment of many waves. The conditions that make that alignment more likely are strong wind, crossing seas, and steep, energetic water. And every single one of those is tied directly to the amount of energy in the ocean, and the energy in the ocean is projected to rise. We are not talking about some brand new monster suddenly appearing in the sea. We are talking about loading the very same dice we have always rolled, so that the worst outcomes come up a little more often and a little more extreme, in precisely the places that were already the most dangerous. And here is the line that ties it all the way back to where we began tonight, to that lonely buoy off Ucluelet and the paradox of the 1,300-year wave in the 30-year record. The most extreme rogue wave we have ever measured arrived in 2020. The trend toward greater severity is already visible in the data we have in hand right now, and the forcing that drives all of it, the warming, the strengthening winds, the rising wave energy, is, by every projection we have, still ramping up. It has not arrived. We are still early, just like the drought that breaks its 131-year record before the El Niño that was supposed to cause it has even fully shown up. The ocean appears to be setting its records before the forcing that should drive them is fully in play. The signal is arriving ahead of the cause. That is the pattern no one is talking about. Not that the waves are everywhere, all the time, more and more. The honest, careful, peer-reviewed version is quieter than that, and to me it is far more unsettling. The giants are growing more extreme even as they grow no more frequent. They are concentrated in the seasons and in the seas where the wind is strongest. And the wind, on the largest scale, is getting stronger. We have a record only 30 years long. It already contains a wave that should take 13 centuries to appear, and the conditions that make such waves are trending, slowly and steadily, in the wrong direction. The record we are setting right now may not be a fluke at the lucky start of a short data set. It may be the early edge of a curve that is only just beginning to bend, and I want to be clear and calm about what that does and does not mean for any of us, because the point of this channel is never panic. It is pattern recognition. So, before we close, I want to give you the honest other side, the counter-arguments, the genuine reasons this might be less alarming than it sounds, because you deserve the full picture, both halves of it, not just the frightening one. Part 6, the honest other side. If I left the story where Part 5 ended, I would be doing the exact thing I warned against at the start of it. I would be handing you the dramatic version and quietly calling it the truth. So let me deliberately turn the ship around and give you the counter-arguments, the real reasons for caution. Because a genuinely calibrated view of this requires holding the worry and the skepticism in the very same hand, at the very same time. The first and the most important caveat is the one I have already pressed on, and I am going to press on it one more time, because it matters more than any other single thing I will say tonight. Rogue waves are not, in the data we actually have, simply becoming more frequent. Along the best-studied coast in the world, over 2 solid decades of records, they were becoming slightly less frequent. So anyone who tells you, flatly and confidently, that there are just more rogue waves now than there used to be, is going well beyond what the measurements support. The careful claim, the defensible one, the one that survives a hard look, is about severity, and about the conditions that drive it. It is not about raw frequency, and I would always rather give you the claim that holds up under scrutiny than the one that makes the better headline. The second caveat is about that phrase we keep returning to. The most extreme rogue wave ever recorded. It is true. And it is genuinely striking. But you have to keep firmly in mind what the word recorded is doing in that sentence. It means the most extreme inside a window about 30 years long. It does not mean the most extreme in the entire history of the ocean. The sea has been throwing up giant waves for as long as there have been oceans and storms to drive them, which is to say for billions of years, and almost every one of those waves rose and fell in some place, at some time, where no instrument was watching, and no person survived to report it. So, when we say a wave is the most extreme on record, we are making a modest statement about the brief span of our own attention. We are not making a grand statement about the deep past. And that 1300-year number, remember, is really a measure of how badly our models underestimated the wave. Our models, as this whole night has shown, have been wrong about rogue waves before, badly and for a long time. The number is a measure of our surprise as much as it is a measure of the wave's true rarity. The third caveat is the one I wove all the way through Part 4, and it deserves to stand on its own and be said plainly. Almost none of the historic ship losses can be pinned on a rogue wave with real certainty. The München is the most accepted case we have, and the evidence of those bent davit pins is genuinely, hauntingly compelling. But even that remains an interpretation, the best reading of a fragment, and not a proven fact. The Waratah is a theory among several theories. The supertanker statistics describe severe weather broadly, not rogue waves specifically. So, when you read a confident headline somewhere that declares a rogue wave sank this ship or that one, the honest truth underneath it is almost always softer and more uncertain than the headline lets on. We believe. We infer. We read the fingerprints as best we can. We very rarely actually know. The ocean, in the end, does not file reports, and the fourth caveat is about rarity itself, brought right down to the scale of any one of us. Even with every single thing I have told you tonight, a rogue wave at any one specific point in the ocean, in any one given minute, is still a rare event. When scientists went back and modeled the conditions around the American cargo ship El Faro, which was lost with all hands in a hurricane in 2015, they estimated that the chance of it meeting a wave with a crest over 14 meters in any 10-minute window was something like 1 in 400. 1 in 400, and that is in the middle of a hurricane, per 10 minutes. So the thing that makes rogue waves a real and serious danger is not that they are likely at any one moment, because they are not. It is that the ocean is almost unimaginably vast, and ships spend days and weeks at a time crossing it, and a long enough exposure to even a 1 in 400 chance eventually accumulates into something close to a certainty. The danger is real. But it is a danger of accumulation, and of sheer scale and time. It is not a wave waiting behind every swell, hunting for you. And there is one more piece of honesty I owe you, because it cuts against the drama in a way that matters. For all the fear in this story, we are, in this one narrow respect, safer than any sailors who ever lived. Not because the waves are smaller. They are not. But because, for the first time in the entire history of seafaring, we can see them coming. We have the forecasts. We have the buoys. We have the satellites. We have, as you will hear in just a moment, the beginnings of an actual equation for predicting them. The sailors on the München had none of that. The crew of the Waratah had none of it. They went out into a sea full of monsters that science swore did not exist, with no warning and no way to know. We go out into the same sea, but with our eyes finally open. The waves did not get less dangerous. We got less blind. And in a strange way, that is the most hopeful thing in this whole dark story. And it is exactly the note I want to carry up to the surface with us. So hold both halves of it together at once, the way a calibrated mind has to. On the one side, The severity is trending up. The conditions that drive these waves are trending the wrong way, and the most extreme wave on record is recent. On the other side, the raw frequency is not clearly rising. Our record is desperately short. Our historical attributions are deeply uncertain, and at any single moment in any single place these waves remain genuinely rare. The truth is not the scary version, and it is not the dismissive, nothing to see here version either. It is the calibrated one, sitting in the live tension between the two, and that tension, that stubborn refusal to round up to panic or down to comfort, is exactly the place this channel is built to live. There is one last way to hold all of this honestly, and I think it is the truest one. Picture two people looking at the very same ocean. The first one hears that the most extreme rogue wave ever recorded happened in 2020, and the severity is trending up, and the forcing is still building, and they decide the sea is coming for us, and they are afraid. The second one hears that the frequency is not clearly rising. Our record is only 30 years long, and most of the old shipwrecks can never really be proven, and they decide it is all overblown, and they stop listening. And here is the thing. They are both wrong in exactly opposite directions, and they are both wrong for the same reason. They each grabbed one half of the truth because one half is easier to hold than the whole. The calibrated view is harder. It asks you to carry both the worry and the doubt at once, without collapsing into either. To say, plainly, the giants are getting more extreme, and we are not sure how fast, and that uncertainty is itself a reason for humility rather than for comfort. That is a harder thing to hold than fear, and a harder thing to hold than dismissal. But it is the only honest place to stand. Which brings us at last all the way back up to the surface, to what all of this was really about from the start.